So after spring break, midterm 2 is coming up quickly next Tuesday. You'll be held in class, same format, closed book, 2 pages of cheat sheets, and roughly same format as midterm 1. I have posted 2 sample problems on the website, so please practice, and solutions will be posted tomorrow, so Wednesday. And Thursday's class, that will be April 4th. We'll do Q&A. So if you work on the sample problems, if you have questions, we can discuss on Thursday, okay? Yes, so topics to be covered in midterm 2 is everything up to today's lecture. So up to today's lecture. And what about materials before midterm 1? We can't completely cut the material away, but the emphasis will be between midterm 1 and midterm 2. Okay, so emphasis on materials after midterm 1. But we use the same principles, you know, KCO, KVO, and so on. So those are all common tools. Any questions about midterm? I have 2 office hours. So one today. The office hour on Thursday, I cannot make it. So I will schedule another office hour maybe next Monday, in case you have last minute questions. So for today, we're going to new kind of systematic discussions of amplifiers. So today we'll talk about single stage amplifier. Single stage means they are 1 transistors. Okay, so stage really means 1 transistor amplifier. So this is the simplest amplifiers, and it is a basic building block. As we go to more sophisticated amplifiers, you can kind of break it down to this simple level. To start with, we like to look at circuit models for amplifiers. Before we talk about circuit amplifiers or models, let's start with something that you have learned in 16AB. This is called 1-port model. Okay, so from 16AB, if you don't remember, it's a good time to review. So you talked about circuit model of 1-port circuit. Okay, 1-port means they are a pair of terminals. So a generic 1-port terminal will be kind of a black box of circuit here. We don't know what's inside, but we can represent the circuit with a pair of terminals. And this pair of terminals, let's call this A and B. So you can apply a voltage, VAB, okay, plus minus, and you can have a current IAB. Sometimes it's convenient to simplify a whole block of circuits by just a very simple equivalent circuit. And there are 2 common equivalent circuits that's being used. And there is a Thevenin equivalent circuit. How many people remember Thevenin equivalent circuit? You do? Is it taught in 16AB? Okay, all right. So Thevenin equivalent circuit is, I will represent this block of circuits by series resistance and whatever voltage source it is there, I will represent it by these two circuit elements. So this is called Thevenin equivalent voltage, and this is Thevenin equivalent resistance. Okay, so this is one representation. Usually small signal. Okay, so a large signal is usually a nonlinear behavior. So these are usually small signal models. Okay, small signal again refers to the AC signals. And there is another circuit, equivalent circuit called Norton equivalent circuit. Okay, sometimes people don't fully distinguish the name for these two different circuits. Okay, Norton equivalent circuit again is a small signal. It's primarily representing a current source. So if you have a small signal current source, it is convenient to represent the circuit with a current source. This will be I Norton current source, and this will be equivalent resistance, Norton equivalent resistance. And it will become clear as we go through applications in circuits, why Norton circuit, when you have a independent current source, it's more convenient to represent it as a parallel resistance. Whereas in Thevenin equivalent circuit, when you have an independent voltage source, it's more convenient to represent it as a serial combination. Okay, everybody's okay with these two equivalent circuits? So I'm sure you have gone through real circuit examples, how to reduce a whole block of circuits down to these simpler circuits. And amplifier is more complicated. So amplifier is generally a two-port circuit, okay? So a two-port circuit, what we can talk about a general two-port equivalent circuit. Because for amplifiers, we care about input and output, therefore, it is usually a two-port circuit. So by now, you know that one port means a pair of terminals. So this is the input port, and this is output port, right? So generally, you have input and you have output. And again, these are small signal models, okay? So these generally apply to AC signal. We will be attaching input on the left side and measure output from the right side. This looks like a symmetric network. However, for circuit, we usually have assumptions about these two-port circuits. So for amplifiers, the assumptions which are generally good is that this is a linear, okay? This is a linear circuit. So if you have a linear combination of input, the output is simply the linear combination of the original outputs, okay? So we talk about linearity. Same as what you learn as a linear time invariant system. Another property that we will assume is called unilateral. That is, signal really flows in one direction, and it's not really possible to flow backwards. So unilateral means, well, the output depends on input, but input is not affected by output, okay? This is generally true. So this is generally true for most of amplifiers. There are some feed-throughs through parasitics. We'll talk about some of those effects as we get more into details once we understand the fundamentals of these two-port circuits. Okay. Questions so far? Yes.
So when there's feedback,
yes.
This is not
that's right. When there is a feedback, well, depends where you put the feedback. If you put the feedback explicitly from the output here to the input, okay, the part that's inside the black box is still unilateral. Yes.
It's a question about the previous Norton and equivalent. When we do the small signal analysis for transistors, we usually do the Norton equivalent when we do the dependent volt current source. Why do we do that with the reflection?
Yeah, so the question is about the equivalent circuit for a transistor where we use a dependent current source. So that is not to be confused with these Norton equivalent circuit where it is an independent current source. This is used to model, for example, you have a function generator, it is a source, and you can model that source as an independent voltage source, or if you have a current signal, you can model that as independent current source. The transistors are the equivalent circuit we introduce is to model the nature of the transistor. That is not the Norton equivalent circuit. That is not the two-port equivalent circuit that we're going to talk about. So the two-port circuit that we are going to talk about includes a transistor embedded in there, includes all the biasing resistors and every circuit that's needed to operate that circuit. The whole thing inside the black box will be reduced to this two-port circuit. It will become clear as you see some examples.
So it's not possible to do that with the voltage source.
It is, as you will see, inside these two-port equivalent circuits, there has to be some dependent voltage or current source. Otherwise, the output is not dependent on the input. So the output will have to be dependent on input. So for two ports, it's very frequent to have dependent current source in here. Okay, all right. So the common two-port circuits depends on the nature of input and output. If we have input, so let's say if the input and output, okay, if the input is voltage, output is also voltage, okay, then we have what we call this a voltage amplifier, okay? So for this will be voltage amplifier. So this will be the type of amplifiers. They are, as you can kind of guess, there are four possible combinations. The input could be voltage. The input could be current, okay? And if the output is also current, okay, then it is a current amplifier. If the input is voltage, output is current, then we end up having a crossing. So you kind of think of the transfer functions. The transfer functions, this will be VO over VI. Here will be IO over II. Both are dimensionless. Here will be IO over VI. So input is voltage. And this has a unit of conductance. So this type of amplifier is called transconductance amplifier. Okay, the unit of this is Siemens. Okay, then there's a final combination. Input is current, output is voltage. So this will be VO over II. Okay, the unit is ohm, and this will be called trans resistance amplifier. Okay, trans resistance. Just basically take on the unit. Trans resistance sometimes more frequently is actually called trans impedance amplifier. Okay, impedance is kind of a generalized resistance. It could include some imaginary part. All of them are used. The last one is used very frequently in communication circuit if your signal is current. For example, in fiber communication, when you detect the signal, which is a photocurrent, then the nature is a good example that the source is current. So the first stage amplifier is a transimpedance amplifier. Okay, so there is the reason we talk about all of them is because well, there is a need for all these different amplifiers. So next we're going to talk about one by one their equivalent circuit. So for voltage amplifier, their two-pole equivalent circuit is like this. There is an input resistance, okay, and there is a voltage amplifier, okay, so there is AV, and the input voltage here is V in, here is AV times V in, okay, and there is a series output resistance here, R out, okay. This looks very similar to a transistor equivalent circuit, but it's not to be confused with a single transistor equivalent circuit. This is a circuit of the entire block. Exactly what it is, after we go over the model, we'll talk about specific amplifiers, okay? And for current amplifier, the two-port circuit is, well, the input part is the same, okay? So we have R in, and now we have a dependent current source, okay? And the dependence will be whatever current coming into the input port. The output is AI times II times I in, okay? The output equivalent resistance is now in series combination, okay? We can go through the other two combinations. So the trans conductance amplifier, yeah, as you can imagine, the input is voltage. So the input port, actually all input port looks kind of similar. So input port is R in, okay? And we have V in here, but the output will be dependent current source, okay? And the dependence, as in a transistor, will have the unit of Siemens. So this is GM, symbol for Siemens, times V in, okay? And the output resistance will be in series. Okay, so here is R out. Okay, noted we use a capital G M. This is different from the small gm, which is the transconductance of a transistor itself. This capital GM is the transconductance of the entire circuit block. Okay, could be different from a single transistor. Yes. So this is just a two-port part, and we will need to attach input. Okay. So let's finish this first. So the trans impedance amplifier, which will have current input. Okay, so there will be I in, and this is R in, and we have now a dependent voltage source. Sorry, I guess I didn't catch your question. What you're suggesting is, yeah, it should be a shunt resistance for the output. Yes, for transconductance, yeah, R should be in the shunt position. Okay, so for transimpedance amplifier, then we have Rm. Okay, this is the trans resistance times I in as a dependent voltage source. Okay, so these four circuits becomes clear once we start to attach input and output. So for the voltage amplifier, the typical input will be a voltage source, okay? And a voltage source will be represented by Thevenin equivalent circuit. So you will have a source resistance, and here is your Vs, right? And output typically, well, is kind of just a load resistance. So let's call that RL here. If it is a current source, we typically reduce the source into a Norton equivalent circuit, okay? And so this will be how we represent the source. Here will be RS, and this will be IS, okay? And output, let's assume we are just driving a load resistor. So it is the same. Okay, similarly for transconductance, we'll be feeding it in with RS and VS. Okay. And output will be RL. And for transimpedance, again, we represented by Norton equivalent circuit, RS, and here will be IS, and driving a load, RL, okay? Now that we attach the source, you can see more clearly sort of the unique functions of these different representation. Here, V in, okay, let me change another color again. So V in for this circuit is simply a voltage divider, right? Vs times Rs plus R in and R in, right? And the output likewise. So let's say here is our output voltage. VO is here. And VO is equal to AV times V in, okay, the dependent voltage source. And then there is a voltage divider, R out plus RL and times RL. Naturally, for an effective amplifier, you want most of your signal to drop inside the amplifier. You want V in to be as close to Vs as possible. So we can talk about the ideal values, okay? Ideal values of this input and output resistance. So for voltage amplifier, you want R in, you want R in to be infinite, as high as possible, kind of like open, okay? What happened when R in is infinite? Well, V in is equal to Vs. So that's ideal case. And what about R out? Well, you want R out to be ideally 0. And when R out is 0, your output voltage is equal to the internal amplified value. So that's kind of ideal. What about current source? Well, it's kind of the opposite. Current source, R in ideally should be 0. So that the current will be dividing between this path here and a path that goes through R in. You want all the current to go through R in. You don't want current to be wasted in the source resistance. This happens when Rin is much, much smaller than Rs, or let's say it's 0, ideally. And Rout, on the other hand, will be exactly the opposite. You want to force the current to flow through RL. You don't want, you want as little as possible to go through Rout. So you want Rout to be infinite. Okay, so now you see the nature of the amplifier. We do need to design the amplifier with the desired input-output resistance. Otherwise, we'll be wasting a lot of input and output voltages in these dividers. Okay, so likewise, transconductance Rin should be infinite. Rout, okay, should be also infinite. You want to drive current here. You don't really need to memorize this. You just draw the equivalent circuit and see where the current or voltage goes, and you can derive these very easily. So for transimpedance amplifier here, Rin here should be ideally 0, so that all current will flow through here. And the output is a voltage divider, so ideally Rout is also 0. So these 4 classes of amplifiers, in addition to what they primarily amplify, the input and output resistance is also a primary design consideration. Okay. Question so far? No? Okay. So then we will. How do we calculate input and output resistance? What does input-output resistance mean? So let's get back to our 2-port circuit. Okay. So how do we calculate Rin? Okay. Well, Rin, we basically just take the 2-port circuit. Okay, and you attach a test source here, okay, VT, which generate IT. You can actually attach a test the current source, or you attach a test the voltage source. It doesn't matter, okay. And importantly, the effect of the load has to be included here, okay. So the Rin is basically equal to VT test the source divided by IT with no RS. You take away RS. You don't want to confuse RS with the circuit that you want to analyze. But the load does affect what the source see as impedance. So you do need to include RL. Okay. Likewise, how do we estimate Rout? So we do exactly the same thing. We short circuit RS just as we do Thevenin or Norton equivalent circuit, but we have to include RS. RL, we take it out because that's the equivalent resistance RL sees. So RL, we take it out and we just attach a test voltage source, okay, VT, and generate IT. This is a 2-port circuit, so Rout is basically VT divided by IT, but this time no RL, but include RS. The reason for including RL, RS makes it really easy when you have multi-stage amplifiers. You just put the blocks sequentially and you just multiply them together. And your RS will be correct. It won't change as you attach the next stage. The next stage will become a load to the first stage. So this is a kind of a high-level way to simplify more complicated circuits so that you don't have to do small signal analysis, KCO, KVL for the entire circuits. That will really drive you crazy, I think. We can try that in one homework. But these are easy way to solve it. So with this in mind, what are the kind of standard form of transistor circuit if we use the simplest circuit, only one transistor? Well, one transistor circuit, single transistor circuit. So noted single transistor circuit, a transistor has 3 terminals, right? Source, drain, gate. But a 2-port circuit has 4 terminals. So this means we have to reuse one of the terminal when we do a single transistor circuit. So, you know, one terminal is used in both input and output, both sides. We call this terminal common. So we refer to this terminal as common. Okay. So for example, the circuit that we have talked a lot about, okay, by now you should kind of remember this. And here is input, B in, okay. This is the output, B out, okay. Well, we are really referring this to ground here. V in is really referring to ground. V out is also referring to ground, okay? So ground is connected to source. Source is used twice. So this is known as a common source amplifier. So this is common source amplifier. Okay, and for a transistor, you can actually be creative. You can actually use common gate. All right, we'll talk about common gate in more detail, but we can have. It looks weird, but you can ground the gate and actually apply your input here. Take your output here. Again, both input and output refers to ground, okay? So gate is common. This is called common gate amplifier, okay? There is also common drain by combination. There are really 3 canonical forms. So common drain amplifier refers to, well, the drain is common. Common doesn't necessarily means they are connected to ground. They are actually connected to VDD. But in AC equivalent circuit, VDD become ground. Okay, so this will be input applied to the gate, but output, you take it from the source. Okay, and these 3 combinations of circuit actually give you reasonable tool set to produce low input impedance, high input impedance, or high or low output impedance. So you have the complete tool set to do that. If every amplifier is common source amplifier, then you don't have the complete tool set to do that. Yes? These are all NMOS, so we can look at PMOS version, okay? We don't frequently talk about PMOS, but certainly you can think of PMOS version. Let me draw PMOS version here. So the source will be on top, okay? And input will be applied here. Output goes here, Okay, so this will be a PMOS common source amplifier. Okay, and common gate amplifier is the same. We always draw source on top side. Okay, and it's common ground here, and V in applied to the source side. Output take from the drain side. Common drain will be similar, okay? And there is a need for both, actually. That's the power of CMOS, not only for digital circuit, but for analog circuit as well. So output will come out here, the output. Okay. Yes, you have more questions? No?
Yeah.
Yes.
When we do the common drain and how do you measure like VM? Is it between like the gate and drain?
We always refer to ground. So implicitly, these are all referring to ground. Why is it common drain? Because drain, VDD in AC equivalent circuit, ADD is AC ground. So in AC, we actually will make it as a ground.
Oh, so the reason is because there's no resistor connected to drain out there. That's why that becomes ground, and that's how we use it.
Yes. Yes. So what is VDD? When we draw this dashed line VDD, it really means it is connected to a voltage source, which is VDD. And when we do AC equivalent circuit, it becomes a short circuit. So it become like this. So this is the AC equivalent circuit. Yes.
If we switch the input and output,
Yeah. So it is unilateral. Remember, when we talk about the transistor circuit, it is unilateral because of the unique transistor characteristics. So input and output, you cannot switch. You can switch. So there are, if you think of it, there are 6 combinations, and we're only using 3. The other 3 is not as useful. Yeah, you can look at what are the other 3, and you can say they are actually not as usable. Now, ideal old-fashioned MOSFET is symmetric. Source and drain are really the same. You can change source and drain. But as technology goes, there are source engineering, drain engineering. So source and drain start to look different. Our simple model, the cross-section we draw, they look identical. In the more modern transistors, they start to diverge. So we don't switch source and drain commonly. So another thing I'd like to point out is, as in the case of a common source amplifier, which we have already discussed, it is actually advantageous to use a current source biasing, okay? And this will become clear as we work through these examples. So this is actually a better implementation in most cases. Common gate, you will have really 2 independent source bias, okay? And this allows you to change input and the output. And as a current source in the AC equivalent circuit, they become open circuit. So it looks like a transistor is just hanging there and connecting just to input and output in the AC equivalent circuit. And likewise, the common drain, it will be usually advantageous to use current source biasing. We'll talk more about current source later. Okay, so just to mention that these are alternative forms that you will see.
Just replacing all the.
Yes, Yes, these are the low resistors. So not every single resistor. There are sometimes other resistor that we will use. Okay, so the resistor, the RD that we talked about there. Okay, RD and RS. Okay. Okay, so these are kind of very high level overview. And one of them will give you low output resistance. One of them give you high output resistance. One of them give you super high output resistance. Okay, one of them give you low input resistance. One of them give you high output resistance. So it is the combination now allow you to really build ideal amplifiers with not just the desired gain, but the desired input and output resistance. Okay, so we already talked about common source, right? And but we haven't talked about the equivalent input-output resistance yet. So let's briefly talk about common source. And let's talk about the resistor version here. Okay, so this is common source amplifier, RD, okay? And you can replace that by small signal equivalent circuit, okay? So this will be VGS, and this is a small GM, VGS, okay? And we have R0 here, okay? And we have RD. RD, remember in the AC is kind of connected to ground. So we have RD here, okay, RD here. The voltage source as a voltage amplifier, so we will be connecting this to VS, right? And this will be V out. So the voltage gain is really easy with this small signal. V out is really equal to the current that flows through, well, the combination of resistor, we can simplify by RO over RD in parallel. So the output voltage is simply GM VGS times R0 over R parallel with RD. And VGS is just equal to VS. So this is just GM times VS times R0 parallel RD. So AV is simply VO over VS, and this is equal to GM times R0 in parallel with RD. So this is the same results as we obtain when we go through more elaborate process. Oh, negative. Yeah, yes, negative. So the current is flowing upward, but its voltage drop is like this. So it is negative. All the values should be negative. Yes, thank you. All right. So what about input resistance? Okay, what about Rin? Well, Rin is essentially the same configuration as this circuit, but for Rin, we will let me redraw it. So we attach VT, and this is IT. Up to this point, you know, we really don't need to draw the entire circuit, okay? We include RL, yes, but here is open circuit. So, you know, you look into nothing, so Rin is infinity, okay? Insulated gate. Okay. Later, when we talk about parasitic capacitance, this is no longer infinite. Eventually, this will be connected to input capacitance, gate capacitance. Okay. So that's easy, easier than usual. So what about R out? R out, we can look at this. So we will ground VS. Okay. So this is grounded now, and we have R0, we have RD, okay, and this is but we don't include RL, right? And now VGS is equal to 0. So basically this says there's no current source here. And when you attach your VT and IT, what do you see? Well, you basically see the linear parallel combination of R0 and RD. So this is also a trivial case that you can simply write R out equal to R0 in parallel with RD. Okay. And typical order of magnitude. So typical values. So R0 will say, well, we typically say it's 200 kilo ohm, okay? RD, well, it's usually a few kilo ohm, okay? Otherwise, you cannot drive the DC bias. DC bias, you'll consume too much voltage in the DC bias if it is too high. So this means R0 in parallel with RD usually is basically just RD. Now you see in the previous two-port models, two of them likes to have output resistance as large as possible. And RD is really small, kilo ohm is very small. So what do we do if we really want high output resistance? So if we replace RD by a current source, right? Then the equivalent RD is going to infinity. Ideal current source have infinite resistance. It's an open circuit, basically AC. In this case, your output resistance will now become R0 in parallel with RD, which is really infinity. So it's basically R0. R0 is not infinity, but it's 200 kilo ohm. It is like 100 times larger than what you get with a circuit element. So that's why the current source bias give you a desirable feature here. Okay, so far so good. Okay, common gate amplifier. Common gate. So this is the first time we talk about anything that's not common source. Okay, so this will look a little bit different. What is a common gate? Let's draw a resistor biased version. Okay, so there will be an RD, okay, and there will be a transistor here, and we'll assume we'll use a current source bias here. So this is I bias, okay, and we'll apply our input here, okay, and we take our output from here, and here normally also have voltage bias source here. You need some kind of V bias here, okay. But if you look at the AC equivalent circuit will be basically RD goes to ground, and we have gate also go to ground, and this is open circuit, and this basically just connected to R in, okay, and this is R out, V out. So it looks like the transistor is hanging there. It is not hanging there. There's a closed loop. Just in AC, the impedance of the current source is so large that we can ignore it. Okay, so if you continue with the equivalent circuit, hybrid pi model, then we will have basically a gate that's grounded, okay. Now the source is not grounded, okay. So source has to be source. Now we will apply. This is commonly used as a current amplifier. So I will use a current source here, okay, IS. And the hybrid pi model is here. So this is GM, VGS. VGS is not equal to 0, even though gate is grounded. Source is not, okay, so VGS is not equal to 0. And we have R0 here, okay? And we have RD that goes to ground. RD goes to ground. Remember, source is not ground now. So R0 and RD are no longer in parallel, okay? So this is the equivalent circuit, and this is V out here, all right. So it is more commonly used for this circuit as a voltage source. So to estimate a current gain, this is more commonly used as a current amplifier. So to estimate a current gain, I make RL equal to 0 first. So basically, I measure the current here. I measure my output current here, I out, and this is actually a short circuit here. So there is RL, okay, to evaluate AI current gain, okay. You basically make RL goes to 0 so that all the current will go through the branch. Let's go back to this two-port circuit. It'll become clear. So this is the two-port circuit. If we want to estimate what is AI, if we want to find out what is AI, well, we have to measure this current, right? We have to measure AI in. But in this equivalent circuit, we also have R out. So there are two current paths. In order to measure that, if we make RL goes to 0, okay, we make RL goes to 0, then all the current will go through this branch. And we can estimate what is this internal current source. So this is what we are doing here. And okay, make RL goes to 0. So now this is a short circuit here, right? And we really want to know what is the current I out that flows through here. The convention of two-port circuit, the current flows into the amplifier. That's why I draw the direction of the current to be flowing into the two-port circuit. Okay, so exactly where is the two-port circuit? The two-port circuit is everything, including here. Okay, so this is a two-port circuit. All right, and because RL is 0, these two parallel combination of RD in parallel with 0, you know, RD, these two branches, RD in parallel with RL, which we make it into 0, is basically 0. So we can simplify our equivalent circuit for estimating the current gain. Okay, it's basically like this. And here is our input, I source, okay? This is grounded. And this basically goes to ground. And this is I out, okay? Okay. So this turns out to be kind of a trivial solution. You can apply KCL here. You apply KCL here. IS is going to flow through both paths, right? But both paths will combine and all go out in a single terminal at the output here. So I really don't need to care how they distribute between this dependent current source and the current flowing through R0. So I can simply say I out is actually equal to IS, but the opposite in direction. Okay, so if you treat the whole thing here in the dotted line as a node, all the current going into the node has to be equal to the current going out of the node. That's the essence of KCL. So basically this means AI, which is equal to I out over IS is -1, is -1. And after you know this, you come back and see the equivalent circuit. They say, of course, gate is insulating. There are 3 terminals. Gate is insulating. Whatever comes out from source has to, whatever goes into the source has to come out from the drain, right? So there's only 2 other terminals. Gate is insulating. And if you simply look at this circuit diagram, you say, of course, all the current will have to flow this way. And current gain is 1. The directionality with the convention, we define the I out to be this way. We define I in to be in this direction, so it's -1. Okay, so I'll have to leave early today. I do like to cover the input and output resistance of the common gate amplifiers, and that's what Ming-Chiang will cover. So I will later on do another roughly 30 minutes of video lecture. I will post that on the web. So for those of you who come to the lecture, you still need to watch the second part. Okay, all right, thank you. Next Tuesday, yes.